Hello everyone. Welcome to today's light reading webinar, which is entitled Virtualizing CCAP, Developing a Distributed Access Architecture. It's broadcast by Light Reading and UBM Tech. My name is Alan Bresnick. I'm a senior analyst at Heavy Reading, the research arm of Light Reading. Based in Toronto, I specialize in the cable and video technology businesses, or the markets for them. I've put together this webinar with a lot of assistance from our sponsors, Cox Communications, Juniper Networks, and Gainspeed. We have an excellent program for you today featuring some fresh, innovative thinking about the evolution of the cable access architecture and network services. In this session, we will explore how cable operators can go beyond CCAP's technology advances and develop a less centralized, more distributed architecture. We will examine the challenges of today's cable access network and see why they're growing. We will look at how the CCAP architecture can be virtualized, and we'll focus on the attributes and advantages of distributed networks. We have just a few housekeeping announcements before we begin, so let's get them out of the way now. First, this webinar contains audience polling, one polling question actually. The polling question will appear in the slide presentation window. Please complete the poll when it appears and click on the Submit Answer button located on the polling slide window. Thanks in advance for your participation. Speaking of participation, you can take part in the Q&A session at the end by asking questions at any time during the webinar. Just type your question into the Ask a Question text area and then click the Submit button. At this time, we recommend that you disable your pop-up blockers. The slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the Download Slide button located below the presentation window. Finally, if you run into any technical problems, please visit our webinar help guide by clicking on the help link below the presentation. In addition, you can contact our technical support helpline, which is also located in the webinar help guide. Okay, so we are moving on. Whoop, we went too far. Let's take a quick look at our three featured speakers today. First, we'll hear from our good friend Jeff Finkelstein. Jeff is Executive Director of Strategy Architecture for Cox Communications. Then we'll hear from Samir Parikh. Samir is Director of Product Management for Gainspeed. Last but far from least, we'll hear from Andrew Smith. Andy is Chief Architect for Cable MSO Networks at Juniper Networks. Okay, now let's look at today's webinar agenda. As usual, we have a lot to cover today. First, I'm going to run through a quick overview of CCAP and where MSOs stand with CCAP and what kind of progress they're making. Then Jeff Finkelstein will take over from Cox, and he'll go into the challenges that are facing cable operators and why they're growing and how they're growing, and he'll also get into some head-end scaling issues, among other things. After Jeff is done, we'll hear from Samir Parikh from Gainspeed. I got this all wrong. Excuse me a second. Yeah, from Gainspeed. Samir will talk about the evolution of the access architecture and also give us a view of what the virtualized CCAP architecture will look like, among other things. Then we'll hear from Andy Smith from Juniper. Andy will talk about the evolution of network services, and among other things, he'll talk about the role of edge routers, the role that edge routers will play there. Then Jeff will come back for a final wrap-up, or as Bob Murphy from the New York Mets used to say, a happy recap, and then we'll get into questions and answers from the audience. So, one other thing, during the webinar we will also conduct one audience poll to gauge your views about the challenges that today's cable access architecture faces. And of course after that we'll address your questions. So it should be a pretty productive hour coming up. Okay. So let's get started by reviewing CCAP. As you probably all know, CCAP stands for Converged Cable Access Platform. The general idea of it is to combine the functions of the CMTS and the EdgeQuam devices that sit in the cable head end. Eventually, it's designed to implement narrowcast and broadcast QAMs, and there are many operational features for scaling the all-digital network. The idea is to cut down on power usage and cooling usage and save space in the head end while combining the functions of the CMTS and the EdgeQuam. Okay, a lot of market drivers to CCAP. I won't go through all of them here. As you can see, there's plenty, but let me just highlight a few of them for you. As I mentioned before, the idea is to make it easier, more efficient, and less expensive to move traffic out of the head end, and also to combine IP traffic and QAM traffic. It's designed also to another market driver is to save head end space and to save power, both electrical power and cooling power in the head end. And also makes it easier to roll out, for cable operators to roll out both DOCSIS 3.0 and soon to DOCSIS 3.1. So you can go through some of the market drivers here and see what else is on the list at your leisure. Then let's talk about where the major MSOs in North America stand with CCAP right now. As you know, probably know, Comcast has led the way, though Cox was also part of the development team for CCAP. But Comcast has led the way with trials and deployment. Comcast has already done an operational trial last year. They also issued an RFP to vendors last year, and they started some small cap CCAP deployments this year with plans to really scale up next year. Time Warner, we believe, is also working on trials right now with plans to do bigger deployments next year, and so are several of the MSOs. Maybe Jeff will tell us a little bit what Cox is planning to do, but Cox is certainly working on it. Rogers, Cablevision, and Charter have all have CCAP in their futures, as well as do some smaller MSOs around the country. Okay, so with that, I will move on to our first main speaker, who is Jeff Finkelstein. As I mentioned earlier, Jeff is Executive Director of Strategic Architecture for Cox Communications. Jeff is joining us live and in color from Atlanta. Good afternoon, Jeff.
Thanks very much, Alan. So what I want to start with discussing is what is really driving us towards not only CCAP, but even beyond. So as we look at where we are with consumer speeds, that there's been a lot of discussions around what's called the Nielsen's Law, which is talking about how we keep growing in this top speeds, or what I like to call the billboard speed that we offer to customers. Now, one of the interesting things is that if you ask people what their speeds are, what we find out is that people are only really concerned about speeds at one point in time. The majority of people, not the technical folks, but the typical residential type consumers, and that's when they are buying a service. So these billboard speeds are absolutely critical. So as you look at it, what you see is that these speeds have been increasing linearly on a logarithmic scale. And we went back and worked with others, have started looking back in the early days of 300 baud acoustic coupler dial-up modems, and just sort of plotted out points on this line. And what we realized as we did this is that in this dial-up era, that we fit this very nicely into this timeline where right around in this 1998, as we were running out of things that we could really do with twisted pair and bonding twisted pair, that this new technology came out, and it's what eventually became known as DOCSIS. And that has taken us for quite a while. And with DOCSIS 1.0 and DOCSIS 2.0, and for those of us that have been involved in DOCSIS for a while, we've seen this incredible growth. And the folks that have been involved in these efforts have just done a bang-up job making sure that it could meet the needs of the consumer. That led us into the DOCSIS 3.0 era. And in DOCSIS 3.0, now we're bonding multiple channels. And it's getting us even more and more capacity. But what we're realizing is that with DOCSIS, looking at where we are today, we've got this sort of 150 megabit service, top tier, that many folks are offering. And this really defines the size of these bonding groups and how many channels we put together in order to be able to achieve this speed. And you may use a 2-to-1 ratio of total available bandwidth to max speed, or maybe a 3-to-1, but that sort of defines what that is. Well, I've kind of realized that when this moves, we can reduce this headroom a little bit if we so choose, if we're willing to accept maybe a little bit of congestion. What really is a problem for us is this sort of parallel line that I like to draw along with this top billboard speed. Now, this parallel line is the weighted average speeds. So if you just take the different speed tiers that you have and the number of customers, you kind of come up with this weighted average speed. And if you look at where we are today, sort of as an industry norm, we're at about 18 megabits per second. Now, you can move that top line without having a tremendous impact on what's underneath it, but if you move that bottom line, you add a lot of capacity because of the sheer numbers of customers. So this really drives the amount of bandwidth that we have in our network. So if we plot out what we can do with DOCSIS, and we look at that, what you see is that for the upcoming 32 by 8 cable modems, you get to this gigabit speed, which is out there in the not too distant future, and then you can see what the total capacity of a 1 gigabit plant is, and it sort of defines where we are in this curve. And what we realize is that if we're really going to grow beyond this, and if we truly believe that that top line is correct, then what does it really mean? It means that eventually, even with 3.0, as wonderful as it has been for us as an industry, we're still potentially looking at some long-term challenges. So I like to call this sort of generation shift that's coming up, kind of jokingly call it the N-squared GAN for the next generation access network, because we called DOCSIS 3.0 next generation. So this is what is going to really be coming next. So what's kind of driving us towards that? What is going to cause us to have yet another paradigm shift in what we do? So as we start looking at where we are with DOCSIS 3.0 and modular CMTS and what we really gain with CCAP. So you can see as you look at this slide that there are so much video equipment in the head end. There's data equipment. There's different components that are out there in our network. And as we look at this, you can see that with CCAP we have a real gain. Just by moving towards that architecture, we reduce not only space, but we have these power requirements. It's going to be less power. We're going to save on cooling. We're going to save on space. Now we move forward from there, and we look at what happens if we go to node +1. So what you see happens in node +1 is, given the constraints of the physical size of the head ends, we can't really fit enough modular CMTS architecture in there. And even the existing video and all the different equipment that we have available. So even with CCAP, it's a challenge. We can find ways if we have to make it fit, but even there, it is a challenge. And then if we go even a little bit further, and let's say, what if we try to go to node +0 to a passive coax scenario? Here we can see that we've even got a bigger challenge. There's no way the existing technology today will fit. And CCAP, even CCAP, as dense as it is still a challenge in this environment. So let's think about the challenges and just sort of sum that up. We've got limitations in the physical space. We have problems with how much we can fit in these head ends. We have problems with power. We have problems with cooling. Now, we could potentially build more facilities, but building facilities is a very costly proposition. So it's something that we do when we must, but we are always looking for better ways of moving that ball forward. So we can look at, there's linear optics limitations, there's distance and cost. We have headroom issues as we go to higher and higher orders of modulation with DOCSIS 3.1. So CCAP does truly help in the short term, but as we progress further and further down this continuum of adding more speeds, adding more bandwidth, moving the weighted average curve, even CCAP starts to have challenges. And it doesn't solve all the optics, all the linear issues that come up with analog optics. So this sort of frames the discussion, and as we look at new ways to solve these problems. And with that, let me hand it back to Alan, and he will introduce the next speaker.
Okay, Jeff, thanks very much. We had that one other slide about guiding principles. Did you want to take us through that one as well? Or
good point. Good point. I'm getting ahead of myself here.
That's okay.
So one of the things that I like to do is I like to set guidelines and have these bumpers. And with those bumpers, it gives us some directional guidance. So what this directional guidance will give us is what our basic rules are. So from here, what I'd say is that our rule number one is centralize what we can and distribute what we must. That you achieve scale not through density, but by decentralization and moving things out that make sense and keeping the complexity in the cloud. Automate everything that can be automated. As we add more and more capacity into the network and more devices, it becomes more difficult to manage. So as we can automate it through capabilities like software-defined networking, that helps tremendously. So silicon matters for scale, availability, and resilience. So that there are things that just make perfect sense in custom ASICs. As you move a lot of packets, just do that through as simple a mechanism as you can. And it's an A-B box, A in, B out, Ethernet in, DOCSIS out, Ethernet in, Wi-Fi out, etc. But the things that you can put in software using advantage of technologies like network functions virtualization give you the opportunity to reduce the cost by moving those cognitive type functions, the things that require processing, into the cloud. Okay, simple modular architectures always win. As we go back to the early days of computing with the IBM mainframe, and we started going through the Super Mini to the desktop, and now a smartphone which has more compute power in many ways than any of the original mainframes had. As we make things more modular, they inherently become simpler, and to make it more simple, it has to become modular. And then the most important rule, I think, is use open standards. That there are places where in this stack where proprietary does have a place, but in order to achieve the scale and the reductions in cost and the simplification, there's a lot of open standards out there, whether OpenFlow, Open vSwitch, Open Daylight, that give us the ability to drive the cost out of it. So with that, let me once again hand it back to Alan.
Okay, thanks, Jeff. I like the next gen, calling it next gen. I think maybe we could come up with something like next gen squared or something like that as a name for the architecture. Well, thanks very much. That brings us to our one and only audience poll of the day. Here's the question on your screens. The question is, what do you see as the biggest facilities and/or optics challenges facing cable operators? The 6 choices are head-end space, head-end power, head-end cooling, distance and cost, RF performance, or SNR, and the ubiquitous other. Now, take a few moments for the ON24 system to collect all the results. So remember, if you want to ask any of our 3 speakers a question while you're waiting, just type your query into the Ask a Question text area and then click the Submit button. In the meantime, Jeff, let's bring you back in here for, I have a question for you. Question is, Jeff? Okay, thanks. Question is, isn't a distributed architecture very complex? And if so, why would we do it?
So one of the things that we thought about early on as we were discussing distributed architectures is, do we really want to move more complexity into the plant?
Right.
And as you think about it, and because of the great work of our silicon vendors, that we've really reduced the PHY to basically a chip. And the Mac, to a large degree, has been reduced to a chip. So these functions have to exist somewhere. Now, if we've reduced it to a single piece of silicon, and eventually I expect that somebody will figure out a way to have both Mac and PHY on a single chip.
Wow, that'd be something.
So as we look at that, do we really need to be concerned with that complexity? Because as operators, we're constantly going out and doing FCC proofs. We're sweeping the plant. We're doing things out there. So we have to be out in the plant at various times during the year anyway. So as we do more with as we do more with adding functions further down the plant, in many ways, because of these newer technologies, while there may be more complexity than we have today, all we're doing is transferring that complexity from the head end out to the plant, and now we're managing it remotely using things like SDN for automation. So it seems like it's an issue, but whether it's a PHY or whether it's the Mac PHY or whether it's the entire CCAP that you would put out there, we're figuring out better ways to manage that, and our technicians in the field are very, very bright folks.
Right.
And they figure out how to make all of this work in the long term for us.
Okay, so it's not so much making things more complex as just moving the complexity to a different part of the network.
Correct, and coming up with better ways in which to manage that.
Okay, very good. Thanks, Jeff. Let's take a look at the results from the poll. We have almost a dead even tie here. They've been running neck and neck. Distance and cost right now is in the lead with 27.8%. Followed closely by head-end space at 25.7%, and then head-end power at 18.5%. I'm surprised by this because when we talk about CCAP a lot, we talk about the problems always being the head-end space and head-end power, so I'm surprised that distance and cost came out as the biggest challenge. What do you think about that, Jeff?
I think it really depends on where you're starting, Alan.
Mm-hmm.
That some newer head ends are going to have possibly more space and may have more power, but the distance limitation in many ways is driven by some of the municipalities and where we have to place equipment. So distance for the optics does have a direct impact on the modulations and what we can actually do with it. Mm-hmm. So going to digital optics is just a next logical step to my thinking as a way to reduce this by reconstituting the RF closer to the customer. We take all the linear issues out of those optics out of the picture, and we end up giving a much better overall experience to our customers.
Okay, very good. Thanks, Jeff. Thanks for explaining all that, and thanks to everybody out there who participated in the poll. Now we're going to move on to the second part of today's presentation. Our next speaker is Samir Parikh. Samir, as I said earlier, is Director of Product Management for Gainspeed. Samir is joining us from Sunnyvale, California. Good morning, Samir.
Good morning, Alan. Thanks a lot. Pleasure to be
Sure.
here. So with Jeff's setup, when we look at how the network and the access architecture can evolve, it's good to kind of step back and start by, let's understand what CCAP is. Like, what's the breakdown, what's the anatomy of a CCAP product? Because that's really the baseline for how we can think about the problem space and come up with some creative solutions. So when you look at the anatomy of a CCAP, we've identified 6 fundamental building blocks. The 2 of them are common building blocks that you find in any IP/MPLS networking device available today. So you've got your IP/MPLS control and data plane, and you've got your subscriber management. So well-known functions available on products available from multiple providers in the market today. And then you have the things that really make it a CCAP, which is your cable-specific capabilities. DOCSIS 3.0 today, 3.1 in the future. Your MPEG video processing as you integrate the edge QAMs into the CMTS to build a CCAP. Your PHY, your physical RF modulation, and then we like to call the cable control plane, the back office interfaces that pull this whole thing together and integrate the system into the way you do subscriber management and billing and provisioning for video and for voice and for data. So when you start out and you look at that, when you can break it down on these components, now let's reimagine how we build these components, how we place them in the network as a whole. So rather than thinking of CCAP as a monolithic system, think of it as a collection of these functions. And by reimagining how we put it together, there's opportunities to maximize scalability of the overall solution, dramatically lower the space and power required. You can start looking at how we leverage industry standard components, Ethernet edge routers, SDN controllers, etc. There's opportunities to how we address the RF performance when you start looking at that that transport layer. And obviously, no new architecture is going to be that successful unless you have a path to lower cost and improve service availability for the operators in the long term. So when you think about it, what is the virtual CCAP architecture? It's how do we take these piece parts and reimagine it? And so, the first step on that is the first logical step is let's take the DOCSIS and the RF processing out of that monolithic system and distribute it out into the field. And so what this allows us to do is we now get rid of the traditional fiber node as you know it and create this concept of an Ethernet node in the plant. By doing that, we're replacing the analog optics. So when the audience poll question about distance and cost, well, that problem is dramatically reduced because you go from proprietary linear analog optics that are very expensive as they scale to standard Ethernet transport that you guys have deployed in mass as you start offering commercial services, cell tower backhaul services. And that really streamlines that architecture. The other big benefit now is we start looking at RF performance improvements because we've pushed RF generation into the field so you don't incur those losses from the head-end combining infrastructure and the linear analog lasers. So huge improvements on how you can now see yourself going from DOCSIS 3.0 to 3.1 and getting that higher order modulation. The next then logical step is let's look at the IP MPLS and the subscriber management capabilities. You look at the edge routing platforms that are available today from pick your favorite vendor. They have all the capabilities necessary to perform that function. It's really just a matter of having the right software layer to kind of wrap around it to make it fit in that cable architecture, in that virtual CCAP architecture. And that's kind of a key part of, again, leveraging industry standard components, reducing complexity, and therefore reducing cost. And once you do that, you kind of couple that with this notion of this cable control plane, which is this software application that is running on that CCAP platform. Now I can move that to the cloud. And then the only piece remaining there in the hub is video processing. Now, because I've moved the RF to the node, my video processing element is no longer a traditional edge QAM. You can think of it as an ether QAM because instead of providing RF output, it's providing Ethernet output. And then that cable control plane that is sitting in the cloud, in the data center, can leverage all the modern techniques of SDN, OpenFlow, and manage and configure this entire system. And it really allows us to pull this together into that kind of combined virtual CCAP architecture. And by doing this, if you kind of look at it, what this really does is it streamlines your overall hub and head end. When you look at what happens, your hub is now just your video platform and your edge routing platform. You don't have a combining infrastructure. You don't have an analog transport infrastructure. So the power space benefit is dramatic. And then, the simplification of the physical network is pretty dramatic. So let's take a look at this architecture and say, okay, well, how does it compare to CCAP today? So if you look at Jeff's example of his head end today, which is N+6, 360 service groups, and you start looking at how I could build that in a virtualized CCAP architecture versus a kind of what I'd call a traditional or monolithic CCAP architecture, there's a pretty significant power and space savings. This architecture is, 75% lower in overall power consumption and cooling. It's about and it's 65% lower in space consumption. But the real kicker is when you scale the network. So when you start looking at the network and say, okay, I want to go to N+1, like in Jeff's example, that CCAP architecture now is you're kind of bulging at the seams in that head end. You've just run out of space. You're just running out of power and cooling. But this virtualized CCAP architecture, actually the space requirements are linear. It's basically the same. So now you're looking at a 90% improvement in power and cooling and an 80% improvement in space. And then we take it to the next logical step and you go to N+0 and the virtual CCAP architecture, the head end configuration is identical. Because all you've done is you've deployed more nodes, you're aggregating them, but the overall system is already scaled from day one in that very small footprint to get you from N+6 to N+0 without having to add any more power, cooling, or space. So in this final form, you're looking at an over 95% improvement in power and cooling and over a 90% improvement in space. So pretty dramatic improvements in how your facilities are run and managed, how they're built. And you can think of this long term as now you have an opportunity to rationalize your facilities plan and maybe rethink how you build out these hubs and head ends. So when you look at that overall virtual CCAP architecture, the key underpinnings is we think of it as a virtual architecture with a cloud-based control. And what that allows us to do is, even though we've taken the functional building blocks of CCAP and distributed them to different components, to the Ethernet node, to the edge router, to the video engine, that virtual CCAP controller in the data center pulls it all together for you. So from an operations and back office management standpoint, it's identical to a monolithic CCAP. You'll configure, provision, manage it the same way. It really unifies it, so you don't have to deal with the complexity of the piece parts. You still get the benefits and the management of the whole. And it's an open architecture, to Jeff's point of how do you, when you evolve the network, you really want to focus on open standards and open architectures. And this is really one of these architectures that allows us to integrate with any sort of piece part. There's an ecosystem of video processing engines that are possible, edge routers, Ethernet nodes, all of that, is part of this virtual CCAP architecture that you can open up and build. And obviously we saw the dramatic improvements in power, space, and cooling. Eliminating that physical CCAP chassis, that physical QAM chassis, that analog transport provides tremendous benefits in power, space, and cooling. And when you look at the analog transport itself, by migrating the digital transport to Ethernet, not only did you lower your transport cost, but the RF performance improvements are traumatic, right? This is what's going to be key to get you to the higher order modulation. So when you start looking at DOCSIS 3.1 and you want to get to QAM 4096 in the downstream and 1024 in the upstream, this is going to be the key innovation to unlock that, because that linear analog optics is really a big bottleneck in that architecture today. So that in a nutshell is how we view the world of CCAP beyond today, kind of a virtualized open architecture that really starts addressing the problems for the next generation network, not the problems of yesterday. And with that, I'll kick it back to you, Alan.
Okay, great, Samir. Thanks very much. To me, it's pretty amazing to be talking about virtualized CCAP when we haven't even seen CCAP rolled out yet. So it's amazing how far in advance you're looking at these things. So it's going to be interesting to see what happens when CCAP gets rolled out and then people start looking at virtualized CCAP as well. Okay, so thanks very much. Now we're going to move on to our final main presentation. Our speaker is going to be Randy Smith, Chief Architect for Cable MSO Networks at Juniper Network. Andy joins us from rainy Philadelphia. Good afternoon, Andy.
Hello, Alan. Yeah, it's pretty wet here in Philly, and hello to everyone on the webinar. My name is Andy Smith, and as Alan said, I'm the architect for Cable MSO Networks at Juniper. And today I'll be talking about some of the potential network architecture and services innovations that become possible in this new distributed CCAP architecture. So in any edge or access network, there's really two halves to the system equation. The first is providing the actual connectivity to the user, and in cable, DOCSIS and HFC have historically provided this linkage. The mechanics of DOCSIS are used to deliver a network data service to the subscriber, but it's actually the service operating on top of DOCSIS that enables a revenue model for the cable operator. DOCSIS predominantly has been used to date to deliver broadband internet access, and this has been a very successful business model for the cable industry. But there exists an enormous amount, There exists an enormous amount of innovation in service provider equipment marketplace that historically, we in the cable industry have had trouble translating, porting, or making applicable to cable access. And in many markets across the U.S. and internationally, broadband services for internet have reached a saturation point. And with the notable exception of the digital divide use case, those who are going to buy broadband internet services have already done so, and any change in that service is usually the result of subscriber churn. And, various techniques have been used by the industry to reduce churn, such as bundling of services or free wireless service and so forth, but ultimately the use case for cable access and for DOCSIS has to evolve past the simple internet use case for the cable operator to open up some new revenue streams. Those types of services are available today on modern edge routers, silicon, and software. The challenge we have is interworking those services into the cable environment. This slide illustrates kind of the current dilemma facing cable operators who want to deliver a higher revenue service on DOCSIS. We should note that there's nothing inherent in DOCSIS itself which prevents its use for advanced network services. DOCSIS will carry whatever data it's told to. And indeed, across the CMTS marketplace today, because of the standards work done in Cable Labs, there's a fairly consistent DOCSIS feature set available from all the CMTS vendors. Different vendors may package DOCSIS equipment in various flavors, but ultimately, from a DOCSIS perspective, the equipment is pretty much interchangeable. That, unfortunately, is not the case in the network services feature set of current CMTS equipment, CCAP equipment. Vendors implement really very different software and network services features. This delta, or the difference between the vendors in terms of network services, forces a compromise in cable operators' architecture and in the services that they can offer for revenue. And we think it fundamentally impedes innovation in cable access networks, which results in a limited or a squelched revenue model for the cable operator. Historically, this wasn't such a big issue when the use case for CMTS and DOCSIS was generic high-speed data. But now that the cable operators wish to explore advanced services and advanced revenue that can come from advanced services, this is becoming a larger constraint across the MSO community. So part of what we're proposing in this architecture is a separation, or to enable a specialization between the access portion of the network and the services actually enabled on the network. Relieving the CCAP device of a network services feature set will enable a wave of innovation in access architecture and device packaging, such that we've explored today in the distributed architecture discussion. The access network becomes a specialized entity focused on the cable part of cable. Innovation in DOCSIS and cable technologies is no longer impeded or artificially constrained by requirements and demands in network services. On the network services side, we're now able to leverage the enormous amount of innovation occurring in edge network software, silicon, in the software-defined network space, and we can now apply this directly into cable access. So what's fundamentally enabling all this innovation is the use of open standards. We're using standard Ethernet between the remote Ethernet nodes and the edge router. The edge router in this architecture performs the IP/MPLS functionality as needed for the particular service that the cable operator is delivering. We should note that this edge router in this architecture can be a multi-purpose device. It'll perform functions that are critical to the cable access system, but it's not a cable-specific piece of equipment. We think this is an important point to make, that when considering a distributed architecture, what remains in the hub is as important as what goes out in the plant. Leveraging the same routing and switching infrastructure as the rest of the network will have benefits in terms of sparing, testing, operational simplicity. Operators could explore new models in terms of hub consolidation, even real estate optimization, transport architectures, basically eliminating the constraints imposed by the legacy analog optical transport can usher in new fundamental architectures for building and operating both the cable access network, but the cable regional networks as well. In many cable operators, the location of the physical hub is dictated by the constraints of the analog laser transport. If we're able to eliminate that analog laser transport and move to open standards such as Ethernet that are simpler and easier to scale, you can picture a very radically different cable metro network. I'll now walk through just a couple examples of services we think become enabled or become much more scalable with this type of architecture. The first would be wholesale VPN. Because of the L2 nature of the remote ether node, selling services in bulk that require an L2 service or a layer 2 service can now become as easy to sell as a regular internet cable modem. This is no longer the exception, it can be the rule. You could deploy a wholesale VPN service that's part of multiple VPNs. You don't require any sort of tunneling mechanism or complex CPE on the customer prem. It's just a standard cable modem. This has been done in various fits and starts with BSOD efforts to date on current equipment, but because of the disparity in feature sets on CMTS equipment, this has been more difficult to sell and deploy and create revenue from than it should be. Another example would be leveraging the DOCSIS and access plant for Wi-Fi and small cell backhaul. DOCSIS is ideal for this kind of application. It's ubiquitous, it's powered, it has bandwidth. But to do it today, to provide Wi-Fi backhaul or even small cell backhaul over DOCSIS requires building an architecture that's agnostic of DOCSIS underneath it and not in concert with it, generally through the use of overlay technologies. Tunneling over DOCSIS has its own problems and challenges, but with this type of architecture, with a move towards a more L2-oriented CCAP or distributed CCAP, this is another very good use case for this type of network. This slide, SDN and NFV, like Jeff mentioned earlier, this is a source of enormous innovation and investment and interest across not just cable, but service provider networks in general. Because we are now able to leverage the innovation that's happening in modern edge routers as part of this cable access ecosystem, it becomes possible to construct an entire new class of broadband services that can generate additional revenue. The insertion of NFV or x86-derived network features such as a parental control, a virus scan, something that the cable operator might write themselves, it now becomes possible. We can take certain classes of traffic and switch them through an NFV service chain. This is innovation that's happening today, on modern equipment, and we will be able to bring this type of innovation to cable as well through this architecture. And the final example that I'm going to show is that of a cloud CPE. There's a lot of interest from cable operators in getting away from deploying a very large router or gateway device into the home. Many cable operators can see a future where there's no longer a set-top box in the home. The set-top box becomes software on a TV set or an app on a personal device like a PC or iPad. And so if we're going to get rid of set-tops in the long run, does it really make sense to deploy another large piece of cable-owned equipment in the home? Cloud CPE means that I will take the functionality that would exist today in your home router and deploy it on software in the cable operator's data center. And the router or the default route for your home would be located in a data center. And if the cable operator wants to deploy a new type of service, be it a new firewall service or some sort of service that manipulates traffic or allows you to VPN to your home or does something with iTunes, those sorts of new services can simply be deployed once in the data center, and you don't have to roll a truck or push new software out to the home. You can also experiment with new services and fail quickly. You could try a new service in a particular area of your cable network, and if it doesn't work, you can quickly revert back to how it was. So Cloud CPE is a larger project in the service provider and the access community, and this is another innovation that we could bring to cable with this type of architecture. So my final slide, we think that historically there's been a divide between cable access networks and modern edge router software and silicon. And we think that this concept of a remote architecture and the concept of an L2 CCAP enables us to bridge these two worlds together for the first time, and enables cable operators to construct a service that's truly new and can truly enable some new revenue models for them, and to move past just delivering simple internet service on DOCSIS. Like I said earlier, there's nothing inherent in DOCSIS itself that prevents it from being used for more advanced services. It's simply the way in which it's been deployed. And we're optimistic that by following this new architecture, we could have some new innovation in the cable access space. And with that, I'll pass it back to you, Alan. Thank you.
Okay, thanks very much, Andy. Thanks for that perspective. Okay, well, now we're going to bring Jeff Finkelstein back for a quick summary before we tackle your questions. So welcome back to the virtual podium, Jeff.
Thank you, Alan. So just some closing observations. That there are many challenges that we face as we deploy these new technologies. But we face these challenges every time we deploy any new technology. The requirements of what we provide our customers are continuing to grow, whether it's new speeds, new services, new products. And we have to take up this longer-term view of it, and it's very difficult because we are, as an industry, we are driven by the problems we're solving today. And the things we're talking about here are us taking this sort of long-term view and saying, just not, what is, the equipment we have today and the products we have today solve today's problems. But as we go back and we look at the history, as this moves forward in time, and we learn from history that these new technologies come out at a pace that matches the needs. And this is just another point in time in which we're looking at it and we're saying the equipment we have today, it's going to solve our problems for a long time. But beyond that, there is going to be this longer-term vision that we have. And the sooner we can move there, that if we had it available today, it makes sense for us to move in that direction. So we've seen that there's problems from a space power cooling scenario, and we do have some help with that using CCAP. But as we continue growing, we still are going to have some issues further down the road that we have to begin to think about ways of addressing. That there's scales that we have to talk about, and we can pack more and more in a sort of monolithic type architecture, and that's served us well for many years. But is that the right answer moving forward? Personally, I think that we need to look at a different way of addressing this problem. And the way I see that really happening is we drill down and we look at the things that make sense to keep in hardware, and we look at things that we can more easily virtualize and take advantage of these new technologies that are getting a lot of press these days. And then most importantly, it's not just that there's a long life left in the HFC plant. There is a long useful life in the HFC plant. It has a lot left to it. We just need to figure out how do we sort of bring it into the 21st century. And what do we have to do to make that happen? And the way I see this is the way to do it is we use modern technologies, modern techniques. Software-defined networking as a way to manage and to break things into their constituent parts, network function virtualization, to take things and spread those across the lower cost commercial off-the-shelf processing powers that are available using virtual machine technologies and hypervisors, and then replace the existing linear analog optics which have served us so well for so many years, and move those into using digital optics and use low-cost Ethernet, which not only gives us the scale that we need on those chip technologies, but also gives us the ability to move these modulation techniques closer to the customer so we get better and better performance. Back to you, Alan.
Okay, Jeff, excellent. Thanks for wrapping everything up. I just had a quick question for you before we get to the audience Q&A. When we talk about short-term, mid-term, and long-term, how many years roughly are we talking about? Like 3, 5, 10 kind of thing? Or what's in your head on that?
No, that's a great question. So it depends on where you are. That if you're still running on a 750 megahertz plant, you're in a different place than those that are running in a 1 gigahertz plant in terms of the amount of spectrum that's available. If you have recently rebuilt your plant and you've put in new laser technology, because analog lasers have come a long way in the past 10 years, you may be at a different place. So there's no one-size-fits-all in any of this equation. And you can look at your current growth, and we all have similar growth rates in user consumption. And that will help find your place on that time continuum that we showed earlier in the presentation.
Okay, I appreciate that, Jeff. Okay, so that concludes the formal part of our webinar. Now it's time for us to tackle your questions. So let's see what we have in the queue so far. In fact, I know we have so many good questions in the queue that some of our speakers have begun trying to answer them already. So we'll get to them in a second. Just as a reminder, to participate in the Q&A, just type your question into the text box located below the media player, and then click the Submit a Question button. Okay, so let's take a look at the questions we have remaining here. So the first one up is, what is the compelling argument for pushing DOCSIS to the node? I think this is one for Samir.
Thanks, Alan. I think what it boils down to is when you push DOCSIS to the node, that's the key of getting rid of that physical CMTS or CCAP device in the head end, right? Because that's the cable coax specific technology that, if you move that out, then everything you have left is just standard Ethernet. And that also lets you get rid of the analog optics and move to 10 gigabit Ethernet optics. So you get tremendous cost savings there and RF performance benefits kind of in the long term. And it's really critical to get you to the higher order modulations in DOCSIS 3.1. So that would be the simple, compelling argument for why you would push DOCSIS out to the node.
Okay, got it. Thanks, Samir. Got another question for you here. What are the space Sure, 2 in a row. What are space cooling and power requirements for the Ethernet nodes plus the 10 gig transport optics?
So that's a great question. I mean, when you look at the 10 gig transport optics, these are standard SFP, SFP plus pluggable optics that are available for any transport equipment today. So those are pretty, as power and space efficient as you can get for transport. And then the overall node itself, when you think about it, the technology we have today in silicon and software, we can do all of the functions we're talking about for the node in the same physical size, same power consumption, same dimensions as a traditional fiber node today. So you're looking at that, a 4x4 fiber node that you're hanging up there from any of your popular fiber node vendors. We can perform all of this functions of the Ethernet node in that same package. So that's the power of where we are today with the silicon that's available.
Okay, thanks, Samir. Now we have a question for Jeff. Jeff, will virtualizing CCAP introduce new security issues that we did not encounter in our current networks? That we do not encounter in our current networks?
So anytime we move things out of a controlled environment, right, we're introducing a new security concern. Mm-hmm. But we've become very good at addressing these, and I think the sooner we take that on and think about, are there technologies today that we can leverage to help support that, whether it's from a physical security aspect, not just a logical security aspect. We need to take that into consideration.
Okay, very good. Thanks, Jeff. Let's take a look at what else we have here in the box. What systems in the architecture shown are ripe for NFV? The head-end, CCAP, analog, transport. Jeff or anybody else?
I can take that one, Alan. This is Andy. We see NFV as being a function that would be implemented on the edge router because NFV, if you're not aware, is a mechanism to take network services that would traditionally be implemented on appliances, like a firewall, load balancer, etc., and virtualize those services onto software using the same kind of cloud scaling tools and techniques we use for data center services, we can now implement in network services. And so we see there being a very complementary benefit between NFV and DOCSIS that we would implement in a coordinated fashion between the cloud controller and the edge router. So the cloud controller would tell the edge router exactly what traffic should go through an NFV service chain, and then the edge router would implement that actually on the data plane.
Okay, that was Andy, right?
Yep.
Thanks. Okay. Another question, this one I think is for Samir. Samir, where are DOCSIS frames generated in this model? In the head end or on the remote node? In the last case, it becomes a DCAP solution. A full DOCSIS schedule then has to be implemented in the node.
Yep. So in the virtual CCAP architecture, the full DOCSIS engine is actually in the node. So that is where we generate the DOCSIS frames. That's where we terminate the DOCSIS frames. So, the person that asked the question is absolutely right. We do have a full DOCSIS scheduler and a MAC process and obviously the DOCSIS PHY in the node itself. But, like I said, with the technology available today, we can scale that and put that in that same package that they have in a fiber node that they're deploying today. So.
Okay. Very good. Thanks. Thanks, Samir. Andy, got a question for you. With all those functional modules spread out over the several entities, how will providers manage QoS, how will people provide and manage QoS?
That's a good question. It'll be very similar to how it works today on a modern CMTS in that the upstream cost is determined by the scheduler, which in this case would be on the Ether node, and the downstream cost would be determined by a hierarchical rate shaper, which in this case would be on the edge router. And coordinating all that would be the cloud controller. So the cloud controller knows exactly what's provisioned in a DOCSIS boot file and can tell the edge router exactly what QoS profile to apply to a certain class of traffic.
Okay, thanks very much. Now, we have time for some more questions before the end of the webinar, but as you've probably seen, I've put an evaluation form on your screens. Please complete this form so we can get some feedback about what you liked and what you didn't like about this webinar. Please also tell us what you'd like us to cover in the future. To complete the form, please press the Submit Answer button on the bottom of the page. Thanks. Okay, while you're completing the form, I'll go ahead with a few more questions you submitted, starting with the next one that I can find here. Let's see. Here we go. I'm having a little trouble getting a look at the questions for some reason. Hold on a second. See if I can get rid of the slides that are in front of me here. Jessica, maybe you could read the next question. I'm having a block on my screen here.
Well, I'll jump in, Alan.
Okay, thanks, Jeff.
So there's a question about when we locate these devices into the field. So where do we put these remote nodes? And the answer is it could really be. It could be an indoor unit where you might house it in a cabinet, or think about an MDU. You could put that actually into the into these cabinets. You could put them into the risers. You even put them up in the ceilings, and because these are small, fiber node sized devices, and you could actually just put them replacing existing fiber nodes. So there's no physical limitations other than making sure that it has sufficient power.
Okay, thanks a lot, Jeff.
You're welcome. You back operational, Alan?
I'm back operational. I appreciate that.
Okay.
How will a distributed architecture impact small distribution hubs? This one is for Samir.
Well, that's a great question, because when you look at the move to Ethernet transport, and by moving DOCSIS to the field, you've gotten rid of any timing constraints that you have between the head end and the fiber node in the field and the consumer in their home. So now you can actually look at these smaller facilities that you've built out to deal with those distance and timing issues and say, I can get rid of them, because with Ethernet transport, I can backhaul that new Ethernet node as far as I need to that main head end facility, getting rid of those smaller distribution hubs, consolidating your facilities, and lowering that ongoing OpEx for running the network. So that gives you the option, when you think of that, rather than the augmentation problem you might have, saying, well, if I have to scale that small hub to meet these new demands that are coming in from a service standpoint, this architecture actually just lets you eliminate it altogether. So tremendous savings from that standpoint.
Okay. Thanks a lot, Samir. Question for Jeff. Couldn't we expect a 10x increase in CCAP densities when the number of service group members moves from 360 to 3600? It seems that we are not considering the CCAP density increases and just using 2013 numbers for needs in 2020.
No, that's a great question, Alan. So I put that back in the category of we've always tried to solve our problems with density.
Right.
And we can keep packing more and more into less and less, and we do get some economies of scale with silicon, and we get to ride Moore's Law. But I think what we're talking about is something much more radical, and we're talking about completely reimagining the way we have been addressing providing products and services to our customers. It's not just having boxes that can give a lot of speed and have a lot of power. We're saying we need to be able to look at this and take these technologies and spread them apart and decompose the functional components of these devices and use that as a way of scaling, because as one of our working criteria is simple modular has really become the way that we're looking at things. And so, yes, we can continue to build things bigger and bigger. And for some folks, maybe that's the right answer. We're not saying this is right for everybody. But as we look at it over time, as we want to upgrade various components, rather than have to go to yet another box, why can't we scale components independent of each other? And that way, we have that ability to just add features and functionality where we need it.
Very good, Jeff. We have time for one more question, and Samir gets the lucky draw on that one. Samir, doesn't replicating the DOCSIS processing to the node level come at a financial cost? Is the logic that this cost would be less than the facility expansion in the head end?
Great question. I mean, ultimately, the short answer is it's absolutely going to be at a much lower cost than augmenting the facilities, because, you're talking about multi-million-dollar projects to augment facilities. But, at the end of the day, the real kicker is the current centralized model, we just don't believe scales to meet the demands that you have. So it's really not a question of, do you add incremental cost? To a certain extent, cost is a zero-sum game, but this actually allows us to dramatically lower your cost, leveraging new technology, and save you that OpEx and CapEx for augmenting your facility. So it's not just about moving cost around, it's about dramatically lowering cost from one bucket and eliminating cost out of another bucket altogether.
Okay, thanks, Samir. Andy, did you want to have any last word on that, or should we leave it at that?
Yeah, I mean, to Samir's point also earlier, I mean, because we were moving to Ethernet, there could be a potential real estate, change in the cable operator's network. You could eliminate probably many hubs, and replace them with either a passive Ethernet gear or even just like a single mode fiber meet-me place. So, getting rid of the constraints of the analog transport can enable some very dramatic shifts in the access network and composition of the regional network as well.
Okay, Jeff, as our cable operator, would you like to have the final word on that? You don't have to.
Yeah, I mean, I really don't have anything to add to that. I mean, I think we've explained, where we're going and what the benefits of this over time become. So I think we're good, Alan.
Okay, very good. Well, I'm afraid that we've run out of time, so I want to thank everyone out there for attending, and I want to thank our three main speakers, Jeff Finkelstein of Cox, Samir Parikh of Gainspeed, and Andy Smith of Juniper, for their comprehensive presentations today. Let's give them all a warm round of virtual applause. This webinar will be archived on the Light Reading website by early next week. Within the next 24 to 48 hours, you should receive a personalized follow-up email with details and a link to today's presentation on demand. So feel free to review the webinar whenever you'd like once you get that. This webinar is copyright 2013 by UBM Tech. The presentation materials are owned or copyrighted by Light Reading, Cox Communications, Juniper Networks, and Gainspeed. These companies are solely responsible for the webinar's content, and the individual speakers are solely responsible for their content and their opinions. On behalf of Light Reading, our sponsors, and our guests, Jeff Finkelstein, Andrew Smith, and Samir Parikh, thanks very much for tuning in. Take care, everybody.